Monosaccharides can undergo two different types of chemical reactions. They can either be reduced or they can be oxidized, much like just a regular aldehyde or ketone. We're going to talk about the reduction first. Reducing or reduction of a monosaccharide produces a molecule that we call an alditol. Let's take a look at an example. So we're going to draw glucose. In the straight chain form, this reaction, the reduction reaction, occurs only when glucose is opened up in its straight chain form. But remember that glucose is constantly opening and closing. So it does exist in this straight chain form. When we do the reduction, there's a number of different ways that we can do the reduction, but the way that you're going to see all the time in sapling is the method that you're already familiar with, H2, with a catalyst like PT or PD or nickel, Ni. And this reaction is exactly like your normal reduction of an aldehyde or ketone. So it's going to leave the whole molecule alone except for the carbon-oxygen double bond. That's the only place that anything is going to happen. And so let's just redraw the whole entire molecule, everything except for the carbon-oxygen double bond, because we know that nothing will happen to the rest of the molecule. Totally unchanged. There. And so this reaction works on the carbon-oxygen double bond. It doesn't remove the bond, so the carbon and the oxygen are still there and they're still connected. But what it does is convert that double bond into a single bond, and it adds a hydrogen to the carbon and a hydrogen to the oxygen. So this is what we get. And this molecule is an example of an alditol. Alditol is not its name. Alditol is its type, like monosaccharide is a type of molecule. This is an alditol. This particular alditol is sorbitol. As a reminder, this came from, we started with glucose. So sorbitol is an artificial sweetener. Now, not all artificial sweeteners are alditols, and not all of them are made from real, quote-unquote, real sugars like glucose. There's a variety of different structures for artificial sweeteners. But you can see how this would work effectively as an artificial sweetener, because as long as it still has the sweet taste, which sorbitol does, because this is not a monosaccharide anymore, because we've eliminated the aldehyde functional group, this molecule cannot be metabolized the same way as a monosaccharide can, which means we cannot burn it for energy, but also it cannot incorporate itself into fat molecules, and it also cannot incorporate itself into glycogen because it doesn't have the right type of structure. So this is how it ends up being an effective artificial sweetener, because our body cannot get any calories out of it, and our body also can't store it. Now, the other type of reaction that we can do on a monosaccharide is oxidation. If we do oxidation of a monosaccharide, this gives us a molecule called, or a type of molecule called an aldonic acid. And we are going to use glucose again as our example for the oxidation. So let's redraw glucose. The OH groups in glucose are right, left, right, right. There are 3 different ways that you're going to see the reagents for oxidation written in Sacchaline. One way is a name, Benedict's reagent. So that is the name of the solution that is commonly used to do this oxidation reaction. Benedict's reagent. You may also see, instead of that, you may also see Cu2+, the copper 2+ ions with OH-. Those are the components of Benedict's reagent. So you could see it written that way. And on some of the problems, it's just giving you Cu2+, not including the OH-, which would be an abbreviated version of writing out Benedict's reagent. So no matter which one of those 3 that you see, again, just like with reduction, oxidation is only going to act on this portion of the molecule right here. So we're going to redraw the rest of the molecule, leaving it alone. And you've done oxidation of aldehydes before, so it's not totally foreign to you. But it has been a while since we did them. So when we do an oxidation reaction, this reaction does not interfere with the carbon-oxygen double bond. This is the reaction that magically squeezes an extra oxygen in between the carbon and hydrogen single bond. This molecule here is a type of an aldonic acid. This guy's name is gluconic acid.